For this video, we are to evaluate the given function along the straight line. But this straight line here has two different combinations, or paths. The first one is from 0, 1 to 0, 5, and then after that, from 0, 5 to 2, 5. This is an example of a situation where we have a piecewise function here, or we are going to add the two paths that would actually equivalent to our singular path, which is a straight line. Okay, so this situation here, talking about this perspective, is that if we have here, say for example, the integral of p of xy dx plus q of xy dy along that path, okay, this is just equal to the sum. If we're going to say here that your C is actually the union of your C sub 1 and C sub 2. Your C sub 1 is the first path from 0, 1 to 0, 5. Then your C sub 2 is from 0, 5 to 2, 5. So you will have here P of xy dx plus q of xy dy for your first path, plus you will have here P of xy dx plus q of xy dy for your second path. So we're going to compute the integral, real integral of each. But of course, as we look for the real integral of each of them, we are going to use a specific parameterization for both. Okay, let's say your C sub 1, your first path, is this first movement. As you can see here, the value that changes from one point to the other is actually the y, but the x value retains itself. This is an example of a horizontal path from 0, 1 to 0, 5. Sorry, not necessarily horizontal, vertical, because the y value changes from 0, 1 to 0, 5. So C sub 1 is a vertical line segment path. So your second path, C sub 2, from 0, 5 to 2, 5, it's actually now the axis that changed its value. Y remains constant from 0, 5 to 2, 5, which means this is an example of a horizontal line segment path. Looking into that perspective, as both of them comprises the movement of, or the goal of the integral using these two paths, we're going to solve them independently and add them later on according to the additivity or the concatenation of points. But definitely we will have two sets of parameterization. Now, of course, both of them will just be similar to this one here. This form, you have P of your x of t, y of t, times the first derivative of your x of t, plus your q of your x of t, y of t, times the derivative of your y dt from A to B. But there will be two versions of this. The first version will be for the vertical, and the second version will be for the horizontal. So allow me not to use subs, because some of references would like to use A sub 1, B sub 1, x of t sub 1. It will just complicate all the rest. Allow me to just separate them into two processes here. But what we know obviously is our P of xy, already given as 3x plus y, it's here. And then your q of your xy is actually this one here, 2y minus x. We will have different forms of your parameters later on, because the parameterization for your vertical line path and horizontal line path is actually different from one another. Also, I might be using here additional page, and this video will be very long, so please bear with me as we were going to discuss this step by step. Let's try to attack first. Okay, here let's separate these two. For your horizontal line path, we'll start with the vertical, right? For your vertical line path and horizontal line path, we'll have different forms of parameters, at the same time values for A and B and the first derivatives. For your x of t, for a vertical line path, let's have a review for that. If you talk about vertical line path, it's the x's that do not change. In short, your x of t is the value of your constant that did not change. The constant here is actually 0, as that is the value of your x. So we'll have here 0. As for your y of t, Since it's the y that changes from 1 to 5, we're going to take it as your t. And take note that t corresponds to your a and b, and your t here earlier changes from 1 to 5. In short, your a is 1 and your b is 5. I'm attacking it automatically. Okay? For your horizontal line path, because it's the y value that did not change, your y value would be that constant. The constant value that did not change, which is 5. So this is actually 5. And since it's your x of t that changes from 0 to 2, so that's your t here. And again, your t changes from 0 to 2, so your a is 0 and your b is 2. Please not be confused with the a and b for both paths. I did not label them sub 1 and sub 2 so that we will not be confused, but generally you may, just to differentiate them. Additional requirement here is actually your first derivatives. So the first derivative of your x of t, which is 0, is just 0. And the first derivative of your y of t, which is t, is just 1. For your horizontal line segment path, the derivative of your x of t, which is t, is 1. And then your y of t, its derivative is also 0. We are not yet done because we are going to look for the p and q functions. Now, instead of x's and y's, will be in terms of t. But since there are two paths, we will have two forms for p and q respectively, because we will be using these forms for both of them. For your p of xy, which is supposedly 3x plus y, okay, it will now be changed into p of x of t and y of t. Instead, you will have here 3 of x of t plus your y, so that's y of t. Okay, so for our vertical line path, your x of t is 0, so you have your 3 times 0 plus your y of t, which is t, giving us t. This is for your p function for the vertical. But if you're going to apply this for your horizontal line path here, 3 times x of t is your t. So 3 times t minus, plus your y of t, which is 5, is a binomial expression 3t plus 5. See, they are different, but they are both p of x of t and y of t, but assigned on different paths. Similarly, our q of x of y is identified earlier, okay, as 2y minus x. So if you would like to come up with the q of x of t and then y of t, you will have here 2 of y of t minus your x of t. Your y of t for your horizontal path is t. So you have 2 times t minus 0, that's 2t. This is just for this portion here, okay? But for your second one, which is horizontal line path, your q of your x of t and y of t, instead of 2y minus x, your y is 5. So 2 times 5 minus your x, which is t. So this is actually identified as 10 minus t. Now, all of the items we need for our integral are identified for both of them. So we're going to solve them step by step individually before we combine them as one. Allow me to add a page here because we really need that spaces here. And allow me to copy these requirements so that we will not be turning page to the other. Okay? So allow me to paste it here. This might this might make this page, oh sorry, I wasn't able to copy that. Let me do it again. This might make the second page actually smaller, or the space would be lesser, but nevertheless we just want this so that we will not be jumping from page to another. We still have the Q, so we're going to copy the Q here. Okay, so copy. Hopefully I can just overlap them. Let me see. So you have here Q. Alright, Okay, so now let us have here the integral for both. Hopefully the space are enough. Okay, so let's solve the integral for, let me remove that. Okay, so the first one, for the vertical line path, this is equivalent to the integral. Your a and b was 1 and 5. Take note of this formula here, this one. Okay, so your a and b is 1 to 5. So 1 to 5 of your p, that's t, simply just t, times the first derivative of your x, which is 0, plus your q, 2t, times the derivative of your y, which is 1 dt. Okay? If you would like to continue this on the other side as well, the a and b is 0 and 2. So 0 to 2, your p is actually a binomial expression 3t plus 5, 3t plus 5, but it will be multiplied to the derivative of your x, which is 1, plus your second is t, 10 minus t, times the derivative of your y, which is 0 dt. Okay, so let's solve them independently. Let's start with this. You will have your 1 to 5, that's 0 plus 2t, or simply you can write here 2t dt, because this is 0, right? So you will have here, by linearity property, 2 times the integral from 1 to 5 of your t dt. We know that the integral of t dt is t squared over 2. So you will have here 2 times t squared over 2 from 1 to 5. We can cancel this now, thereby making here 5 squared minus 1 squared, which give us 25 minus 1. The answer is 24. This is the integral only for the first, okay, component of your piecewise function. Now for the second, you will have here the integral from 0 to 2. So you will have here 3t plus 5 still, because that's just 1. But the second here would be 0, right? This is dt. Applying the linearity property, 3, integral from 0 to 2 of your t dt, plus 5, the integral from 0 to 2 of your dt. So your t will follow this one. So we will have here 3 times t squared over 2 from 0 to 2. And we know that the integral, let me place here at the top. You know that the integral of dt is just t itself. This we have here plus 5t from 0 to 2. Substituting the required boundaries, let's start here. So we have here 3, 2 squared over 2 minus 3, 0 squared over 2, plus 5 times 2 minus 5 times 0. That's 0. This is also 0. So we have here 2 squared is actually 4. Divided by 2 is 2. So 3 times 2 is 6. Hopefully that's okay. Again, 2 squared is 4. Divided by 2 is 2. Times 3 is 6. You have here plus 10, which gives us 16. This is the answer for the second movement when moving from straight line 0 to 5 to 2, 5. Now, since these are just part, as mentioned here, since if C is C sub 1 and U sub, C sub 1 union with C sub 2, and we know that they are connected, so we can use the additivity property where we simply add the individual integrals. So we'll have here simply the final answer is equal to 24 plus 16, which would give us 40. Yes, the answer here is 40. This is now the integral of the given function along the two paths, straight line from 0,1 to 0,5, that's the vertical line, and then from 0,5 to 2,5, the horizontal line, which is just connecting both of those paths. So our answer here, as mentioned, is 40. Again, we have two versions of parameterization and two components of our final real line integral. Thank you very much for watching.